So number 1 says find the exact value without using a calculator. Use identities rather than a reference triangle. So when I do this problem, I'm going to try to do this in such a way that I don't have to draw the XY axis at all. I don't have to rely on like all silly turtles crawl. I'm not going to think about where some function, like what quadrant something's positive or negative in. I don't want to use any of that. That's all kind of using a reference triangle. I want to do this purely by using identities. So when I look at this, the first thing I'm going to do is I'm going to look for an identity that involves only cosine and tangent in it, because I would like to figure out the exact value for tangent. Or at least in a way involves only cosine and tangent. So while we're doing this, my suggestion to you would be to have your identities, like the notes with your identities in them, have those out. When I ask these kinds of questions, go back and look through them, look at the identities, try to figure out like which one of those is going to be the one that's useful. This first one, it's a little bit tricky. I would look specifically at the Pythagorean identities. Is going to be the one that we're going to want to use. How many of you look at those and say there's not one that involves only tangent and cosine? Do you agree with that? Well, it can involve so which one is the closest one to that? Either P1 or P3, right? P3 is going to be the one we want, because what's the relationship between cosine and secant? They are reciprocals, right? So I can use, say, which one is it? R5 to say secant of theta is equal to 4. Right? If cosine and secant are reciprocals, if cosine's 1/4, secant is 4. And then I put this sheet up on PowerSchool. I don't know if you guys noticed it when you looked at chapter materials, but this is a list of the identities. And I've labeled them with like letters and numbers to just be able to communicate better to you guys when we're doing these sorts of things, like which identity I'm using. Now, if I use the third Pythagorean identity, so I call that P3, that says tangent squared theta plus 1 is equal to secant squared theta. Because we know what secant is now, I can plug 4 in for secant. And I know that tangent squared theta plus 1 is equal to 4 squared. If I solve for tangent, I get that tangent theta is plus or minus the square root of 15. I did a bunch of steps there all in one. Right? I subtracted 1 from both sides and then square rooted both sides. Now, I'm going to use the fact that tangent is negative in this problem to settle this as that tangent is equal to exactly negative square root 15. Is everybody okay there? Okay. It's given to me in the problem. It says tangent theta is less than 0. Okay. So, yes, Colette? Sure. Okay, so now I have the exact value for cosine and the exact value for tangent. I'm still looking for, though, the exact value for sine. So what I'm going to do now is I'm going to look for another identity that involves sine, cosine, and tangent. And I'm going to use that identity to solve for sine. Ben? Sure. Yeah, the first quotient identity that says tan theta is equal to sine theta over cosine theta. Now to solve for sine, I'm just going to multiply both sides by cosine theta. And I know cosine of theta is 1/4. Tangent of theta is negative square root of 15. So I have negative square root 15 over 4 is equal to sine theta. So we end up using 3 identities on that problem, right? Are we ready to move to the next one? Questions about what we did here? All right. Let's look at the next one. So just like the previous problem, I want to start by finding an identity that involves just cosecant and cotangent. So look through your identities and see if you find one that involves just cosecant and cotangent. James? Yeah, it's the second Pythagorean that we found, right? So that's 1 plus cotangent squared is equal to cosecant squared. Oops. I guess in this problem we gave the variables were alphas. So I'm going to substitute in the value for cosecant. And then when I solve for cotangent, negative 3 squared is 9, and I subtract 1 from both sides, I get 8. I square root both sides, I get plus or minus the square root of 8. And when I simplify that, I get plus or minus root 2 over 2. So I skipped some of those algebra solving steps there, just in the interest of conserving some space. Everybody okay to hear? Since I know that cotangent is greater than 0 in this problem, really this answer is just 2 root 2. Everybody okay with that? Now, I'm going to look for an identity that involves all three, secant, cosecant, and cotangent. That's why nobody's answering this. So this is an aside. We only wrote down this version in class, right? We could also write down this version. And that's what I'm going to use here, is that cotangent is equal to cosecant over secant. That's on the identity sheet that I put on PowerSchool. If you haven't printed that off, I'd print it off and stick it in my notebook or whatever. It's nice to have when you're doing these problems, everything in one place, so you don't have to go flipping back so much. I meant to print these off and hand them to you today, but I had a lunch meeting that I forgot about. And then a bunch of kids come see me this morning that I wasn't planning on. So my whole day kind of went whoop right out the window. You know, just happens sometimes. Okay. So if I want to get secant by itself, I'll multiply both sides by secant theta to get rid of the fraction. I guess we're alphas is really what we're supposed to be doing. I'm not going to go back and change all the rest of those thetas to alphas. And then divide both sides by cotangent. And now I'm going to fill in. So cosecant alpha is -3. Cotangent is 2 root 2. But this is not the way that I'd want to leave my final answer, right? What would I want to do here? Is to rationalize my denominator. So that guy there is my final answer. So these problems 1 and 2 that we just did could be done other ways, right? We didn't have to use identities to do these. There's other ways you could approach these problems. In 3 through 6 or whatever, we now give you the option of using an identity or reference triangles. Let's do this first one using a reference triangle just to kind of refresh our memory of what that's going to look like. So I'm going to start by drawing my XY axis and labeling all silly turtles crawl. And I'm going to start first by looking at the fact that cosine is positive. I know cosine is positive in these two quadrants. Then I'm going to look at the places where cotangent is negative. I know that if a number is negative, then its reciprocal is also negative. So cotangent is negative wherever tangent is negative. So that would be this quadrant and this quadrant. Everybody's okay there. All right. So the reference triangle I'm going to draw then is in this fourth quadrant. Remember, when I draw these reference triangles, one side of my reference triangle must be the x-axis. I would never draw a reference triangle where one side of it is the y-axis. Just to kind of keep that in mind. Now I'm going to go back to the fact that cosine of theta is 3/4. Remember that cosine is adjacent over hypotenuse. So the adjacent side is 3, and the hypotenuse is 4. I can then use the Pythagorean theorem to solve for the other side. When I do that, I get, plus or minus the square root of 7. Because I've drawn this triangle in the fourth quadrant, the vertical part of this triangle should be negative. Everybody okay there? Now I have everything I need to write the values for the other 6 or the other 5 trig functions. So sine is opposite over hypotenuse. Cosecant is the reciprocal of sine. And then I'd want to rationalize my denominator there. Secant is the reciprocal of cosine. Cosine we already have. I'm not going to write it down again. Tangent is opposite over adjacent. And cotangent is the reciprocal of tangent. And when I rationalize that denominator, I have that. So there's the other 5 trig function values that I got by using a reference triangle. That's usually pretty easy, right? As long as you get the angle in the right quadrant and make sure the sign on your sides are correct, everything should be pretty easy. Let's do the same problem using an identity now, just to contrast with you what that looks like, Angela. Sure. I'm going to erase my picture. I'll be slow on erasing the other things for those of you that are still kind of writing things down. Okay. So just like before, I'm going to look for an identity that involves both cosine and cotangent. Which one would I use? Well, there's not one that directly involves cotangent, but I do have one involving secant and tangent. So that's what I'm actually going to use here. So I'll use P3 again. When I plug 4/3 in for secant squared, I get 16/9. And when I subtract 1 from both sides and square root both sides, I get tan theta is plus or minus square root 7 over 3. And because I know that, tangent is negative, I have this. So let's pause for a second. I have cosine, I have secant, I have tangent, I can use R6 here to say that cotangent theta is negative 3 over root 7, or rationalize negative 3 root 7 over 7. So that's 4 of them. The last 2 I need to get are values for sine and cosecant, right? So I'm going to use, say, Q1. I know that tan theta is equal to sine theta over cosine theta. Or if I multiply both sides by cosine theta, I can say that. Cosine is 3/4. Tangent is negative 7 over, or negative root 7 over 3. The 3's are going to cancel. And then I have my value for sine. And then I can use the fact that sine and cosecant are reciprocals. And when I rationalize the denominator, I get negative 4 root 7 over 4. We okay on this one? Okay. I'm going to skip the next several and go down to the last one in this section, which is, I think, number 6. Because it's a little bit different there. What's different about this? We have an undefined. Yeah. So I'm going to start by doing the identities because actually the reference triangle is a little bit tricky what to do with that. So we know already that secant is 1. So that's that. If I use R2, the fact that sine and cosine are secant and cosine are reciprocals tells me cosine is also 1, right? Okay. I know cotangent is undefined. What does undefined mean, though? It's going to be something divided by 0, right? I'm just going to put a 1 there. I don't really know what that numerator is going to be, but I know it's going to be something divided by 0. So if I use then R3, that tells me tangent and cotangent are reciprocals. So tangent is 0 over something. So that means tangent is 0. Everybody's okay there? Okay. Should probably give me a little indication of how you know that, whether it's that work exactly or if it's some other explanation. And now I just need to get sine and cosecant, right? So I'll use, say, Q2 because it's going to connect both tangent and sine and cosine. So if I fill in the values, then I have 0 is equal to sine theta over 1. So sine theta is just 0. And if I use my reciprocal, R4, what's the reciprocal of 0? It's not 0, it's undefined. That wasn't so bad with the identities, right? The only tricky part to that was making that observation that undefined really means it's something over 0. So the reciprocal of undefined is basically 0. That was the only tricky part there. Okay. So if we try to do this using the reference triangle, let's see what happens there. I know that secant is hypotenuse over adjacent. And since that's equal to 1, that implies the hypotenuse is 1 and the adjacent side is 1. Right? Everybody's okay with that idea? Is that possible to draw a triangle whose longest or whose hypotenuse is the same length as its other? Let me retract. It's possible to draw a right triangle where one leg is the same length as the hypotenuse? No. So can we draw a reference triangle for this? No. What we can do, though, is I can use my unit circle definition to deal with this problem. So if I recall, secant is equal to 1 over x on the unit circle. So if this is equal to 1, that implies that x is 1. The only place on the unit circle with an x-coordinate of 1 was this point right here, 1, 0. Okay? That's all I need. Not super obvious what you would do if there was no triangle you can draw that you had to go to the unit circle. If I do that, I know that sine theta is y, so that's 0. Cosine theta is x, so that's 1. Tangent theta is y over x, so that's 0 over 1, that's 0. Secant, oh, we already have secant theta. Cosecant theta is 1 over y, so that's 1 over 0. That's undefined. And cotangent theta is x over y, so that's 1 over 0, and that's undefined. So again, doing this as a reference triangle wasn't difficult, but knowing what to do when you can't actually draw a triangle, or a right triangle, that maybe wasn't entirely clear that I should go to my unit circle definitions there instead of trying to draw a reference triangle. Right? That was a little bit tricky there. Although once you've seen the trick, it's not difficult to do, but making the realization that that's what you needed to do was not obvious. Right? It's only after doing the same math for 15 years that those things are obvious. Do we feel a bit better about these first kinds of questions here? Yeah, probably enough to where at least you could give the rest of them that we haven't gone through a good go. Let's move on to the next type of questions. So these simplifying questions. And personally, as the math teacher in the room, I'm more interested in your ability to do this kind of question than I am the previous sort. I think that these ones here scale into more important questions later on, more so than the other ones do. Okay. So, if I'm going to be simplifying one of these things, what I would like to, or what I can do is I can do algebra things. I can combine like terms, or FOIL, or factor, or make a common denominator, or, do things like that. Or I can use an identity to make a substitution. This problem here has just one term with two factors. Is there any algebra thing I can do with this? Definitely not, right? It's just basically one thing sitting there. What am I going to do with that? Nothing. What I am going to do is look at my identities then. So, should I look at an identity for cotangent or an identity for sine? If I were you, I would look for the cotangents. Basically, the way I kind of think about these problems is that the sines and cosines are kind of like primes. You don't really want to change something from being sines and cosines unless it, or just sine or just cosine. It's rare that you'd want to change that into something else. More often than not, you'd want to change the other one. So let's weed down our list because we have a lot of identities to choose from. Which ones are going to be some worthless identities for this problem? So the Pythagoreans aren't going to be useful here. Why not? There's no squares and there's no plus ones, right? Not going to be helpful for us. Okay, what else won't be helpful? Will the cofunction ones be helpful? Definitely not, because there's no pi over 2's anywhere, right? Stop talking, please. Will the odd-even identities be useful? No, because I have no negative signs anywhere, right? So really, I'm going to be looking at the reciprocal or the quotient here. Everybody agree with that? Which one from there would I want to use? Colette? That's the one that I would be looking at, because it has another sign in that prop, or in that relationship. So that's cotangent. And there's that sign. I'm going to write that sign as a fraction, because if I'm going to be multiplying fractions, it's often helpful to like think about, you know, the sign u as a fraction there. And what do you notice can happen here? By the way, that was Q2 that we used. What can I do here? Yeah, I can reduce, right? And what am I left with then? Cosine u. Can I do anything more than that? No, I'm down to a single trig function. That's as good as life gets. So we're done. That wasn't so bad, right? Let's look at the next one. When I look at that, something jumps out at me immediately. There's an identity that I want to use straight away. Brockton? One of the what ones? The co-function. Yeah. So specifically, I want to use that tangent pi over 2 minus theta is equal to cotangent theta. Or I guess cotangent x in this case. So this is, call that C6. All right. So we did that. What do you want to do next? I see something algebraic to do next. Colette? Yeah, so we can do some reducing, right? Everybody agree with that? Maya? Sure. What do you guys want to do next? There's still a little bit more we can do. Okay. So we want to change cotangent to cosine over sine. At the same time, what else should we do then? Change cosecant to 1 over sine, right? Now, to divide fractions, I just multiply by the reciprocal. And I can reduce. And I'm left with cosine. We okay there? I want to point out to you that there's a little bit of a quicker route than doing this. So if I had instead used that cosecant, or that cotangent is cosecant over secant, that's the other version of Q2. I can reduce, and I'm left with 1 over secant, which is the same thing as cosine. So, same idea, right? You did the same thing. The way that, was it James that made that suggestion? Yeah, either way of doing it is fine. James's way works perfectly fine, no problem with it. Pretty good? Okay. Let's go down and do number 9 then. Let's look at number 9. Is there any algebraic things to do? No. So I'll probably look for an identity. Oh my goodness. I keep wanting to say your sister's name. It's not your name though. Allison. Jeez. I could not, once that Meredith got in there, I couldn't get it out. Okay. So we know that P1 is sine squared plus cosine squared equal to 1. So if you subtract cosine squared from both sides, we know that sine squared is cosine squared minus 1. So maybe I'll call this like P1 star or something, because it's P1, but we did some, like we rearranged it sneakily a little bit. Everybody okay with that? And then what do? We can just reduce. And we're left with just sine x. Alternatively, you could use P1 without rearranging it. So I'm going to use the fact that 1 is equal to sine squared plus cosine squared. You could think about it that way as well. So that's the 1, and then I still have the minus cosine squared over sine. Those guys cancel each other out, and then those guys reduce, and we're left at sine x. Again, same way. Either approach is fine. They're both doing the same thing. We use the same identity. You know, close enough. 10. There's a fast way to do 10, and then there's every other way to do 10. Well, let's see if you can see what the fast way is going to be. Take a look at it. I can do this using 3 steps and 4 identities. Wait a minute. Did I say 4 identities? Only 3. My apologies. What do you guys think? What can we do here? It's quite sneaky, the first step, but if you get the first step, oh, you'll see. Let me give you a hint. It's algebraic. Where are you going to use P1 at? There's not a sine squared or a cosine squared or a 1 in there. My first step I would do is algebraic. It's not a common denominator, although that's not a terrible idea. What does that mean? Okay, what's the greatest common factor you see there? Secant squared? What's the greatest common factor? Tan x, right? Everybody see that? Everybody okay with that? And you're probably looking at me like, why in God's name would I do that? Well, what else can I write 1 over cosecant squared as? Yup. And what can I rewrite cosine or 1 over secant squared as? I can make that cosine squared. And now, Brockton, what do I use? Yeah, P1. So what does that do? Sine squared plus cosine squared is 1. So you're just equal to tangent. Now, doing it the long way isn't that much longer, but it's longer enough. This is pretty slick. I like this. In fairness, I didn't see this right away as the easiest way to do that until first hour when we did it. We just did it the long way that they suggested. And halfway through, I was like, oh, I see the sneaky way of doing this. It was pretty exciting. Should we do it the other way? Maybe the obvious way? Okay. Ben? Yeah. Sine squared plus cosine squared is 1, right? That's what P1 did. All right. So, the obvious thing to do is probably just to use Q1 to write tangent as sine over cosine, and then to use my reciprocal identities to write cosecant squared as 1 over sine squared, and secant squared to write 1 over cosine squared. That's probably the obvious thing to do as your first step, to just write everything in terms of sines and cosines. Then we'll divide these fractions, so that means I'm really multiplying by the reciprocals. Oops, that's not squared. Everybody okay there? What do you want to do here? How many of you would say, let's reduce here? I would not do that here. Why would reducing this here be a bad idea? More steps. Specifically, what are you losing when you reduce here? You're losing your common denominator, right? So if you reduce here, the next step you'd have to just make a common denominator and put it back. It's very obvious that you'd want to try to reduce there if you don't look at the whole thing. That's why I wanted to take a moment to point that out right away. Okay. So, if I do that, I get sine cubed plus sine x cosine squared x all over, cosine. Everybody agree with that? Still chugging along. What do you want to do now? Keep that numerator. What do you see going on in there? Colette? How many of you see a greatest common factor in the numerator? That's what you need there, is a greatest common factor. It was an algebra step, not a trig step. Yes, Colette. And then sine over cosine is tangent. So my warning to you guys, more often than not, the step that students get stuck on these problems are the algebra steps, not the trig steps, right? Every time we sat there waiting for you to think of something, you were looking for identities when you should have been looking to fact or something or whatever, right? So be careful about that. How are we doing time-wise? 5 minutes. You want to try to do one more? Okay. Which one do you want to pick? We got 4 left. Anybody with a preference? 13? Okie dokie. All right. So hopefully, first thing you would do is stop talking, please. And then if I combine like terms, I have 2 sine alpha then what? Well, like I've said before, I usually don't want to convert sines and cosines to something else. That leaves only tangent to work with. If I use Q1, I can write tangent as sine over cosine. Oops. Alphas. And that's going to leave me with 2 sine alpha minus sine alpha, which is just sine alpha.